10th standard ICSE Chemistry Chapter 3A, Acids, Bases and Salts. Introduction can be cancelled. Definitions. Acid. An acid is a compound which, when dissolved in water, yields hydronium ions as the only positively charged ions. Cancel this equation. Let's go for the main equation here. HCl, hydrogen chloride, is a gas. When you dissolve it in water, it forms hydronium ions and chloride ions. This is called ionization. Let's understand what exactly happens here. Here we have HCl, which is a polar covalent compound. They are sharing a pair of electrons, but it is more towards chlorine and far away from hydrogen. So hydrogen develops a slight positive charge and chlorine develops a slight negative charge. So it is a hybrid between an ionic and a covalent bond. So we call it a polar covalent bond because we have two poles, positive and negative. It is not an ionic bond like NaCl, where Na actually gives away the electron. Here they are sharing electron for the namesake, but not symmetrically. This is explained in detail in chapter number 2. Water is also a polar covalent bond, or rather it has polar covalent bonds. So like dissolves like, HCl will be able to dissolve in water. Water will break this bond between H and Cl. Hydrogen cation will be formed. In fact, when you dissolve any acid in water, hydrogen cations are formed. But the hydrogen cation doesn't remain as it is. It gets kind of stuck to this lone pair of electrons of oxygen, and a hydronium ion is formed. So any compound which, when dissolved in water, gives a hydronium ion is called an acid. That's the definition of an acid. But note that hydronium ion should be the only positively charged ion produced in this reaction. There are some compounds, for example, sodium bicarbonate. When you dissolve this in water, it will split up into 3 ions: carbonate anion, hydrogen ion, which will obviously become hydronium, and even sodium cation. So we have 2 cations being formed from this. So we can't really call it an acid because an acid should produce only hydronium ion as the cation. We can call this an acid salt. More about this later. Now the definition of a base. A base is a compound which reacts with hydronium ions of an acid to give salt and water only. That's a neutralization reaction. So you can say base is opposite of acid. Usually metallic oxides or hydroxides are bases. But there is one exception, ammonium hydroxide. Even that is a base, even though it is not a metallic oxide or hydroxide. So we have a base, copper oxide. When it reacts with an acid, it forms salt and water only. The word only is significant. Only then we call it a neutralization reaction. Similarly, here there's another base, copper hydroxide. It is reacting with sulfuric acid. Why do we call it an acid? Because when I dissolve this in water, it will give me hydronium ions. Hydronium ions are the identity of an acid. All the properties of an acid are because of the hydronium ions. The litmus color changes to red because of hydronium ions. So here again, a salt and water are being produced, a neutralization reaction, proving that copper hydroxide is a base. Many bases are insoluble in water. So these are the examples of those. But there are some bases which are soluble in water. They have a special name, alkalis. So all alkalis are bases, but not vice versa. An alkali is a base which dissolves in water. So how do we define it? Well, it is a compound which, when dissolved in water, gives hydroxyl ions as the only negatively charged ions. So just like hydronium was the identity of an acid, hydroxyl is the identity of an alkali. Example, sodium hydroxide, aqueous, that means dissolved in water. So water will break the bond and you'll get sodium cation and hydroxyl anion. That's the only anion being formed here. If there was any other anion being formed in this reaction, we won't call this compound an alkali. And we will come across such compounds soon. Examples, we have sodium hydroxide and potassium hydroxide. They are strong alkalis. And we have calcium hydroxide and ammonium hydroxide. They are weak alkalis. Note that calcium hydroxide is very sparingly soluble in water. Now let's classify acids and bases. First of all, on the basis of the source. Acids which are derived from plants are called organic acids. Citric, oxalic, tartaric, acetic acid. Acetic acid, in fact, can be used to make vinegar, which is used in cooking. So we can eat it. So organic acids are not very strong. Even citric acids are consumable. and so is tartaric acid. Inorganic acids are derived from minerals. Example, hydrogen chloride when dissolved in water forms hydrochloric acid, sulfuric acid, nitric acid. These are quite strong acids. Next, on the basis of molecular composition, hydracids will have hydrogen and a nonmetal other than oxygen. So there will be no oxygen in these acids. So hydrochloric acid, hydrobromic acid, hydroiodic acid. Note that when they are not dissolved in water, they are just gases, not acids. Oxyacids, well, they are acids containing hydrogen, one more element, and oxygen. So oxygen is involved in this. Example, nitric acid and sulfuric acid. Now let's classify acids and bases on the basis of their strength. The strength of an acid depends on the concentration of the hydronium ions present in the aqueous solution of an acid. That means if you dissolve an acid in water and you get a high concentration of hydronium ions, then it is called a strong acid. For example, sulfuric acid, nitric acid, when they are dissolved in water, the solution contains almost entirely ions. So most of the molecules ionize to give you ions. Hardly any molecules remain intact. We use the word ionize here because in this molecule, there is a polar covalent bond. There were no ions available here. The water broke the bond and ions were created during this chemical reaction. On the other hand, when we dissolve, let's say, NaCl in water. Now, NaCl is an ionic compound. There is already a cation and an ion present in NaCl. Water simply separates them. That is called dissociation, which happens in this case, in cases of alkalis. So here, Na is cation, hydroxyl is anion. So when you dissolve it in water, the ions are simply separated. No new ions are being created. So this process is called dissociation. You will study more about these processes in chapter 2. Now, in acids, ionization takes place to give you a high concentration of hydronium ions. So they are called strong acids. But there are some weak acids which ionize only partially. For example, when you dissolve acetic acid in water, so aqueous has to be mentioned, dissolved in water, not all the molecules will ionize. Like most of them will remain as intact molecules. Very few of them will break up to give you hydrogen ions or hydroxyl ions. Right now, if you speak about it in language of hydronium or hydrogen ions, it's one and the same. So here the solution contains molecules as well as ions, both. So it is called a weak acid. Other examples are all these organic acids and even carbonic acid. Please note that anhydrous acetic acid, and anhydrous means without water, it forms crystals on cooling, and that is why it is called glacial acetic acid, because it looks like a glacier. Similarly, let's talk about alkalis. Now the strength of alkalis depends on the concentration of the hydroxyl ions, obviously. So a strong alkali would be the one which has a very high concentration of hydroxyl ions. That means when you dissolve sodium hydroxide or potassium hydroxide in water, they dissociate almost completely. Like 99% of the molecules get split up and you get hydroxyl ions. So the solution has mostly only ions, no molecules are left behind. So these are examples of strong alkalis. Cancel this sentence. Weak alkalis, on the other hand, as you can guess, it means that they have low concentration of hydroxyl ions because they dissociate only partially. Notice that for acids we use the word ionize because they have covalent bond, and for alkalis I use the word dissociate because they have ionic bond. So the ions are separated, and that's why it's a weak alkali. So learn the examples of strong and weak alkalis. Next, let's differentiate on the basis of concentration of acids and bases. Concentrated acid, they have a relatively high percentage of acid in aqueous solution. And dilute acid, they have a relatively low percentage of acid in its aqueous solution. Use this language only. We cannot say that in concentrated acid there is more acid and less water, and that in dilute acid there is more water and less acid. Such a language is incorrect. We are not comparing the two, that is the solute and the solvent. We simply have to say that when the acid has a relatively high percentage of acid, for example, if you have a glass of water and you have added 10 tablespoons of sugar in it and dissolved it by stirring it, you have a concentrated sugar solution because it will have a relatively high concentration of sugar. On the other hand, in a glass of water, if you've added just a pinch of sugar, then it would be a dilute sugar solution because it won't even taste very sweet. So it's all relative. But more specifically, for acids, we can say that if the concentration is less than 1 mole per liter, it is a dilute acid. Mole is a unit of amount of substance. You'll study more about it in chapter number 4. Similarly, we can define concentrated alkali and dilute alkali as well. Now, there is a GR you should write down in your book. Dilute sulfuric acid is surprisingly stronger than conc sulfuric acid. Yeah, conc sulfuric acid has relatively more acid in the same volume of water compared to dilute sulfuric acid. True. But here we are talking about the concentration of hydronium ions. So in dilute sulfuric acid, there will be a higher concentration of hydronium ions compared to conc sulfuric acid. So that's why we say dilute sulfuric acid is stronger. Various factors affect this, which we don't have to get into right now. Just remember this GR. Now let's discuss the basicity of acids and the acidity of bases. The basicity of acids is defined as a number of hydrogen ions which can be produced per molecule of the acid in aqueous solution. Cancel the rest. That means if I dissolve an acid in water and from one molecule of HCl I get one hydronium ion. So I'll call hydrogen chloride, that is hydrochloric acid, as monobasic acid. And the basicity is 1. On the other hand, if we have sulfuric acid, when we dissolve it in water, from one molecule, we get 2 hydronium ions. So sulfuric acid is a dibasic acid and its basicity is 2. And phosphoric acid, when dissolved in water, gives you 3 hydronium ions per molecule. So it is called a tribasic acid and its basicity is 3. Now in the definitions, make sure you cancel the unnecessary words and you replace the word dissociate with ionize, because acids cannot dissociate. They always ionize in water. A give reason out here. Notice that acetic acid actually has 4 hydrogen atoms, H3 here and 1 H here. So when they dissolve in water, we should not expect that it will form 4 hydronium ions from one molecule. No. Only one of them, that is this one, is ionizable. So it's a monobasic acid. Similarly, sulfuric acid is a dibasic acid because from one molecule, both the hydrogen ions can be separated. So we can get 2 hydronium ions, which will be a 2-step process, by the way, but the steps are not important. You can cancel that. Only the net reaction is important. But this also means that if we were to neutralize such an acid with some alkali like sodium hydroxide, there are 2 ways in which the reaction can go forward. First, out of the 2 hydrogen ions, only one of them will be replaced with the metallic cation. The other hydrogen will remain as it is. So H2SO4 has become HSO4. One hydrogen is kicked out and its place has been taken by the sodium cation. This is called partial replacement. On the other hand, if we have excess of sodium hydroxide, see earlier it was insufficient, but if we have excess of sodium hydroxide, then both the hydrogen ions will be replaced. Both will be kicked out and instead we will have 2 sodium cations out here. So that is called complete replacement. Now here, this salt is called a normal salt because if I dissolve it in water, it will not give me any hydronium ions at all. There is no hydrogen left in this. However, this salt is an acid salt. It has a replaceable hydrogen ion. If I dissolve this in water, it will give me a hydronium ion. Remember earlier I gave an example of sodium bicarbonate. Even that was an acid salt because it had hydrogen, and when we dissolve this in water, it will give hydronium ions. So it will give some of the acidic properties like turning litmus paper red. Then why don't we call it an acid? Well, because an acid should give hydronium ion as the only cation. But here, when we dissolve this in water, it will give sodium cation as well. So we can't call it an acid. So we call it an acid salt. So normal salt is formed by complete replacement of the replaceable hydrogen ions in an acid with a cation. And acid salts are formed by partial replacement. Notice that in a monobasic acid, partial replacement is impossible For example, in hydrochloric acid, there is only one replaceable hydrogen. We can't partially replace it. So only normal salts can be formed from monobasic acids. Acid salts cannot be formed, it's impossible. Acid salts can be formed only from dibasic or tribasic acids. So these are the examples of dibasic acids because all of them have two replaceable hydrogen ions. And phosphoric acid can form normal salt as well as acid salt. So out of the three replaceable hydrogen ions, if one or two are replaced, then the salts will be acid salts, namely monosodium dihydrogen phosphate and disodium hydrogen phosphate. But if all three are replaced with a cation, then we call it trisodium phosphate, which is a normal salt. But this is not important, so we can cancel it. Also here the steps are cancelled, and remember, a tribasic acid will ionize in 3 steps in aqueous solution. Similarly, we can define the acidity of bases as the number of hydroxyl ions which can be produced per molecule of the base in aqueous solution or in molten solution. Make the molten state, that is, make the change in the definition. This molten state was not mentioned in an acid's definition here because all acids are soluble in water, but all bases are not soluble in water. So if there is a base which doesn't dissolve in aqueous solution, then how will we know how many hydroxyl ions it can produce per molecule? Well, in that case, we consider its molten state. So if only one hydroxyl ion is being formed in aqueous or in molten state, it is called monoacidic base, and the acidity is 1. Make the changes in the definition, and remember, here we use the word dissociates, not ionizes, because bases or alkalis have an ionic bond. So these are examples of monoacidic base. These are examples of diacidic base because they have 2 hydroxyl ions per molecule which can dissociate when dissolved in water. But some of them can't dissolve in water. For example, copper hydroxide, zinc hydroxide, they can't dissolve in water. Well, in that case, let's melt it. So no water is involved in the fused state or molten state. Still, they will give 2 hydroxyl ions, proving that they are diacidic base. So again, make the necessary changes and cancellations in the definition. And even here, there is a correction. Aqueous, impossible. Copper hydroxide doesn't dissolve in water. Triacidic base, well, they dissociate in aqueous solution or in molten state to produce 3 hydroxyl ions per molecule of the base. By the way, here it won't take 3 steps, it's just a single step. You take fused aluminum hydroxide, that means molten at a high temperature, and it will dissociate to give you 3 hydroxyl ions per molecule. So that's called triacidic base, and acidity is 3. So these are 2 examples of that. Now, formation of the hydronium and hydroxyl ions from acids and alkalis. Arrhenius theory is cancelled, but Lowry-Bronstet's theory is very simple. Acids are proton donors, bases are proton acceptors. So that is a different take on the definition of acids and bases. For example, hydrogen chloride or hydrochloric acid is an acid because it can give us a proton. That is, hydrogen ion is nothing but a proton. And ammonia is a base because it can accept a hydrogen ion, that is a proton. Now, how are hydronium ions formed? I have already explained that water and hydrogen chloride are polar covalent compounds. There is some charge separation between them, and the electrons, shared electrons, are not symmetrically distributed between them. Anyway, when dissolved in water, the bond will be broken and ions are formed. The poor hydrogen ion will become an orphan because the electron that it had and which it was sharing with chlorine will take away the electron and run away. She will now become a chloride anion, and hydrogen will be electronless, just a proton, an orphan. And then the water feels guilty about it, and so it decides to give shelter to the proton. The hydrogen ion will get stuck to its lone pair of electrons. You see that a pair of electron which does not participate in any bond formation is called a lone pair. So if hydrogen sticks here, its duplet is completed. But that doesn't affect the water molecule at all because oxygen's octet is still intact and these hydrogens duplet are also satisfied. So it doesn't matter to them if hydrogen is also coming along with them for a ride. But that also means that since hydrogen was positively charged, now the entire particle will be positively charged. It's called H3O+, and that's how a hydronium ion is formed. Notice that the other lone pair of oxygen is still available, but no, it's not so generous that it will allow one more hydrogen ion to get stuck here. It has its limitations. on its magnanimity. Another way to write this is using this arrow, which shows a coordinate bond, which you have studied in chapter 2. You see, this is a covalent bond, sharing of electrons. Covalent bond, sharing of electrons. But here, they are sharing electrons. But both the electrons are being contributed by one atom. The other atom is not contributing anything. It's come here for free. So such a bond is called a coordinate bond. And that's how a hydronium ion is formed whenever an acid is dissolved in water. Now let's see how hydroxyl ion is formed. Take a basic gas. Ammonia is the only basic gas in your syllabus. It is also a polar covalent compound, so it will dissolve in water. But instead of water breaking its bond, which is quite strong, the opposite will happen. Water, the great divorcer, will itself undergo divorce. That means its bond will be broken, and hydrogen cation and hydroxyl anion will be formed. Again, who made this hydrogen ion an orphan? Ammonia. And ammonia has this lone pair of electrons, so it will give shelter to the hydrogen ion, and hydrogen will get stuck here. So again, we have a coordinate bond here. We have 3 covalent bonds and 1 coordinate bond. Of course, this is not a molecule. We call it an ion because it has a charge, and this is how ammonium ion is formed. What about the rest? Well, hydroxyl, she steals away that electron from hydrogen and becomes an hydroxyl anion, and that's the identity of alkalis. So this is an example of how hydroxyl ions are formed when alkalis are dissolved in water. One correction out here is change the word large to significant. You see, ammonia is a polar covalent compound simply because there is some difference in the electronegativity of nitrogen and hydrogen, due to which the shared pair of electrons are attracted more towards nitrogen. That's why it becomes slightly negatively charged. If it was a huge difference, then it would have been completely transferred, which happens between metal and non-metal and forms ionic bond. All of this is explained in chapter number 2. Next, preparation of acids and bases. Well, there are 4 ways of preparing acids. First, from nonmetals. When they react with hydrogen, they form the acid, respectively. Second, take an acidic oxide, which are usually non-metallic oxides, and dissolve them in water. You get the respective acid. So sulfur dioxide dissolved in water forms sulfurous acid. Sulfur trioxide in water forms sulfuric acid. Phosphorus pentoxide in water forms phosphoric acid, a weak acid. And carbonic acid from carbon dioxide. Notice that carbonic acids and sulfurous acids are so unstable that we should put a reversible sign here. Another method of creating acids is from the salts. Notice that these are all acidic oxides, but there are some neutral oxides also, like carbon monoxide, nitric oxide, and dinitrogen oxide. These are non-metallic oxides, but they don't dissolve in water, or if they do, they don't form acids at all. So they are neutral oxides. Now, if you want to form an acid from a salt, you can use conch sulfuric acid. This is explained in detail in sulfuric acid chapter, which is chapter 7c. Conch, because conch sulfuric acid has a special property. It reacts with a salt, a normal salt, and it's very non-volatile, which means its boiling point is quite high, but it will react to produce a volatile acid. So if it reacts with a potassium nitrate or sodium nitrate, it will form an acid salt. We call it an acid salt because it has an hydrogen ion yet, and it gives you nitric acid vapors. So put the vapor sign here. Similarly, if conch sulfuric acid reacts with sodium chloride or potassium chloride, it will give hydrochloric acid vapors, or you can say hydrogen chloride gas. And if it dissolves it in water, obviously it will be hydrogen chloride acid or hydrochloric acid. Now make sure that the temperature in these cases is less than 200 degrees Celsius. There are various reasons why we should not exceed 200 degrees Celsius. First of all, higher than 200 means it's a wastage of fuel. The glass may crack, and also the reaction will be slightly different. Instead of forming an acid salt, a normal salt will be formed, like sodium sulfate and potassium sulfate. Now that will get stuck to the glass apparatus, and it's very difficult to remove that crust. All of this is explained in the respective chapters of nitric acid and hydrochloric acid. Now the fourth method of formation of acids is by oxidation of nonmetals. So you take conch nitric acid. So mentioning the word conch is compulsory in these equations, because if it is not mentioned, then it is assumed that the acid is dilute, and in that case such a reaction won't happen. So only conch nitric acid has the ability to oxidize the nonmetal sulfur and give sulfuric acid. That's the opposite of what we did here. Here we are using a volatile acid and we are getting a non-volatile acid. Of course, two more products are formed. Nitrogen dioxide gas is formed, which is reddish brown in color. Next, the formation of bases. First of all, from metals. You react it with oxygen, a metallic oxide is formed, and metallic oxides are usually basic oxides. However, there are some metallic oxides which are amphoteric as well, like aluminium oxide, zinc oxide, and lead oxide. Another method of forming a base is take a basic oxide, dissolve it in water, and you will get a base that is a hydroxide. In fact, since they are soluble in water, they are alkalis. If you take active metals, very reactive metals, like potassium and sodium, they will react with water vigorously and give you that alkali directly. And hydrogen gas is released, which burns with a pop sound. So this is a simple displacement reaction. Third method is from salts. If you react sodium hydroxide with salts like aluminium chloride or iron sulfate, you will get a normal salt and you will get a base. But this time the base will be a precipitate, insoluble in water. And they will even have a particular color, which is very useful in analytical chemistry, which we shall study in chapter 3b. And the fourth method is by decomposition of salts. If you take lead nitrate and you heat it, then you will get lead oxide, which is a base. Every metallic oxide and hydroxide is usually a base. And two more products are formed. If observations are asked here, you can say first of all that a residue is left behind which is yellow when hot and yellow when cold. In fact, when hot it is reddish yellow or buff yellow. A gas, a reddish brown gas, which turns green acidified ferrous sulfate solution brown. And another gas which rekindles a glowing splinter. Also, a cracking sound is heard, that is, a decrepitation sound is heard. So I just gave you 4 observations for this equation. All of this is there in practical chemistry. You see, all the chapters are so interlinked. There is repetition of the equations, and hence I will be repeating things and linking things with other chapters. Now, the properties of acids and bases. Well, the physical properties are acids are sour to taste, and mineral acids are very corrosive, and they turn blue litmus red. For bases, they are bitter to taste in aqueous solution, and caustic alkalis are very corrosive. So this is caustic potash and this is caustic soda. That is their common name. And they turn red litmus blue, but only alkalis can do that. But what is the chemical proof or chemical test for acids, for hydronium ions in a solution? Just because the litmus paper turns red, we can't conclude that it is an acid, because it can even be an acid salt. So here are the chemical tests. First, neutralization reaction cancelled. This is a proper test. Reaction with an active metal. So when you add a dilute acid to an active metal that is above hydrogen in the activity series, you will get salt, and you will get a gas which burns with a pop sound, that is hydrogen gas, proving that it was indeed an acid. So this is a simple displacement reaction. Another test will be reaction with bicarbonates or carbonates. Cancel the first 2 equations. That is not a chemical test. Whenever you add a dilute acid to carbonates and bicarbonates, carbon dioxide gas is always released. That is, a colorless gas is released which turns lime water milky but has no effect on acidified potassium permanganate solution, or you can say acidified potassium dichromate solution. So this proves that the gas is CO2, and this proves that the solution is indeed an acid having hydronium ions. Why do we talk about acidified potassium dichromate or potassium permanganate? Well, because SO2 also turns lime water milky. More about this in practical chemistry, chapter number 9. Now, what is a chemical property of bases, or a test that a solution is an alkali, that is, has hydroxyl ions? Now remember, alkalis always react with ammonium salts on heating and give out ammonia gas. Ammonia gas is the only basic gas in our syllabus, and it turns red litmus blue, but that is not a sufficient test for ammonia. We should even say that it turns Nessler's reagent brown. Or another test which we'll study in chapter 9 is that when a glass rod dipped in ponc HCl is brought near it, it gives dense white fumes. And by the way, those dense white fumes are ammonium chloride. But coming back to this equation, you can see here that a less volatile base is giving you a more volatile base, which is ammonium hydroxide. Ammonium hydroxide is not stable, so it will decompose to form ammonia gas and water. And we know the test for ammonia. So this is a proof that the solution given to us is an alkali, that is, it has hydroxyl ions. Only then will it react with ammonium salt to give us ammonia gas. Another test could be to react it with a metallic salt. because when they do, they give us a insoluble hydroxide, a precipitate with a particular color, proving that it was indeed an alkali. Now remember, baking soda formula is NaHCO3 is amphoteric. You may think that NaHCO3 has an H, so it's an acid salt. True. But when dissolved in water, it forms an alkali, a very weak alkali as well. The exact reactions need not be learnt. All you need to remember is that because it is amphoteric, which means it can behave like an acid or a base, it can be used to neutralize the acid in a bee sting. So if you are ever stung by a bee, use some basic substance like baking soda and apply it on that sting area. You can even use a toothpaste, because even toothpastes are basic in nature. Now we know that neutralization is simply an acid and base exchanging their ions. It's a double decomposition or double displacement reaction, giving salt and water only. Heat of neutralization cancelled. Uses are not important, but good to learn the uses of all the acids and the bases. Acidity in acid rain. Reference means out of syllabus, just cancel it. Now let's talk about indicators. Well, they are weak organic compounds, which could be acids or bases, which change their color in accordance with the pH of the solution. What is pH? Well, it's simply speaking the power of hydrogen. It determines the hydrogen ion concentration of the medium, which tells us whether it is an acid or a base, and also it tells us how strong or weak an acid or an alkali it is. And the color of the indicator can help us identify it. So pure water is neutral, so it has very few hydrogen and hydroxyl ions. But if you add an acid or an alkali to it, then you will get a lot of hydrogen ions, or you may get a lot of hydronium ions if it is an acid, and hydroxyl ions if it is an alkali. The pH value tells us the strength of the acid or alkali. The scale is from 0 to 14. But how do you define pH? It's a very technical definition. It is the negative logarithm to the base 10 of the hydrogen ion concentration expressed in moles per liter. How is it exactly calculated? That we need not worry about at all. Just remember this definition and you will apply this in higher standards. Now remember, when the pH is exactly 7, then we say it is neutral. If it is less than 7, it's an acid. And the lower the pH value, the more acidic it is. So 0 means highly acidic. And more the pH value, it is more alkaline. So 14 means highly alkaline. Whereas 8 and 9 would simply means a weak alkali. So such a universal indicator is better than a common acid-base indicator like litmus, because litmus only gives us two colors, red and blue. So it can tell us if it is an acid or an alkali, but it cannot tell us how strong an acid or an alkali it is. Whereas a universal indicator has such a range of colors which gives us an idea about the pH range. So that's the primary difference between common indicators and universal indicators. So only the first point is significant. Second and third point is just the repetition, so just cancel that. And learn the examples of the common acid-base indicators, and also how do they change their color when an acid or an alkali is dissolved in it. These sentences are cancelled and changes pink to red. That means methyl orange will turn red when an acid is added to it. Phenolphthalein is colorless when it is neutral, and even if acid is added to it, it still remains colorless. That means it's not really useful in identifying an acid. What we can do is make it alkaline, and so it will become pink. And if you add an acid to it, it will get neutralized and it will become colorless. Then we can prove that what we added was indeed an acid. What are the uses of the pH values of the indicators? It can help us to know the pH of the soil, which is useful for growing crops. It can help us to know the pH of milk, so we can know if the milk has turned sour or not. In a biochemical and organic reactions also it is useful. In medicine as well, because urine and blood have a particular pH. So if it is different from the range, that means something is wrong with our health. These values need not be learned, so cancel them. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.